Okay, we're recording. Okay, so this is my audience. We're going to make sure we get everybody in there. There's definitely 3 people. Okay. Alright. So, my name is Dylan Barth, and today I'm going to talk to you about my research in cancer growth. But first, I'm going to tell you a little bit about cancer. The World Health Organization did a research survey and came out with the result that 8.2 million people died of cancer in 2012. New cases are expected to rise 70% in the next 2 decades. The American Cancer Society said that cancer is the second biggest cause of death in America. Now, I'm not just telling you these things to depress you, that's why I do research. This is a really pressing and important topic, and it's really important that we understand it at a fundamental level. So, what I do is I work with equations. I work with mathematical models that represent how a tumor grows. And there's not just one, as you can see. This is the graph of all 7 of them. And each 7 of these equations basically has its own merits. And researchers do kind of whatever they want with them. If this curve represents what I want to happen with my study the best, then I'll choose that one. And that's not a really good way of doing science. So what I do in my research lab is I work with lots and lots of data sets to figure out in which cases does each of these curves apply. So the 3 basic things I'm going to talk about today are the different equations, why we need to organize them, and what I do to organize them. So the different equations are, I'm just going to run down really quickly what they do here. This top one is an exponential curve. It goes really fast. This one right here is the Bertalanffy curve. That's just named after a guy, and it has a little bit more biological accuracy. This one right here in green is a linear curve. It starts out exponential, and then it turns off linear. This one right here is the logistic curve. It levels off, and as you would expect a tumor to, stops growing at some point. This one right here is the surface model. What it does is it says that all the cells in the middle of the tumor are dying, and the only cells that are growing are the ones on the surface, on the outside of the tumor. So as you can see, it grows a little bit more slowly than the ones that don't have anything to do with that. This one right here is the Gompertz equation. It's like the logistic equation, but as you can see, it's not symmetrical along this line here. It has a big curve here and a little curve there. There's not really much other difference than that. And then this one is a generalized exponential, and that is basically just a more generalized form of this, and it usually grows a little bit slower. So why we need to organize all of these things is because it's a rampant problem within the biomedical community to not put a lot of thought into which one of these equations you use. So if you have liver cancer, you're really wanting something like this curve here that doesn't give a very big tumor, rather than this one that you only have 20 minutes to live. So we need to organize these because it is the key to understanding what is going on in tumor growth. We want to know in which cases certain things apply. And the other thing that we can do with this information is we can test drugs mathematically. We don't have to use human test subjects. We don't have to put anybody's lives in danger. We can use math to do all that. But not unless we figure out in which cases these equations apply. So what I do, in a very general sense, is I go and find data of how people's tumors grow. This usually happens when people do research, and I just go look at their control groups, which means that there's no drugs given to whatever this thing is. It might be a rat, it might be a person, it might be in a petri dish. And what I do is I run some program software that I and a couple other colleagues wrote, and we see which one of these curves has the closest fit to that data. Then we go and find out a little bit about the kind of cancer that we took the data from. So is it liver cancer? Is it pancreas cancer? Is it breast cancer? So on and so forth. And we figure out which parameters have to do with which equation. In the end, we want to be able to take a sample from a person. We want to have a patient come in with cancer. We want to be able to take certain parameters from them and say, this is what your tumor is going to look like soon. We have this much time to act before it gets really, really serious. So hopefully in the future I'm able to implement this and get my work published and help the furthering of understanding tumor growth. Thank you guys.